Okay, we're back with the video involving the mean value theorem. I'm going to start, I'm planning with this being one video, might be multiple videos depending on how this goes, because the mean value theorem is the most complicated of the three. And the reason being is that we really have to focus on both parts of the mean value theorem, the hypothesis and the conclusion. And the hypothesis for all three theorems is very important. But the hypothesis for the mean value theorem, again, you have it on your paper, actually has two parts to it. And that second part is very important. Okay, but before we actually get into this, let me ask you this question to think about. We're going to take another trip to Route 24, starting in West Bridgewater High School's parking lot. You get in your car, you drive down Route 106, get onto Route 24, and then up to the top and onto the Route 128 over to the South Shore Plaza in Braintree. Okay, and over the course of this trip, the time that you spent on 106, the time you spent on 24, the time you spent on 93, and the time you spent on Route 37 right outside the South Shore Plaza. When you put it all together, you figure out that you traveled on average 53 miles per hour. Okay, on average, during that trip, you went 53 miles per hour. So here's my question. At some point during the trip, if your average speed was 53 miles per hour, did you at least once travel exactly 53 miles per hour? What do you think? And the answer is yes. If your average is 53 miles per hour, and we had a continuous function here, that's what's happening with your speed, you had to actually have traveled 53 miles per hour for at least one instant. In all likelihood, you traveled more than 53 miles per hour more than once. Okay. In all likelihood, what happened was you were going less than 53 miles per hour as you're going down 106. You hop onto the entrance ramp, and sometime on that entrance ramp onto 24, or maybe right as you got into 24, you went from say 40 miles per hour up to 65. So during that time, the intermediate value theorem says you had to have hit 53 once. Okay, so you hit that 53 once, and then you were 65 for a while, and then as you were exiting the Beltway and onto the ramp to get to the South Shore Plaza, your speed probably dropped from 65 down to say 20 miles per hour, something like that. All right, and again, to get from 65 down to 20, you had to hit 53 by the intermediate value theorem. So you actually hit it twice. Okay, but when you take the slow speeds at the beginning and at the end, along with the very fast speed in the middle, the average was 53 miles per hour, and that means that you had to have hit 53 miles per hour at some point. Okay, that's basically what the mean value theorem is saying. Okay, but now let's break it down a little bit more. Okay, so if we look at the hypothesis of the mean value theorem, we see that two things have to happen. One, just like for the previous two theorems, on the closed interval from A to B, okay, our function must be continuous, all right? No breaks, no jumps, no gaps. If that happens, all bets are off. Mean value theorem doesn't guarantee anything, okay? That's the first part of the hypothesis. The second part of the hypothesis says that not only must the function be continuous on the closed interval from A to B, but the function must also be differentiable on the open interval from A to B. Okay, so remember, differentiable means that you can take the derivative. All right, and when we talk about on a graph, there's three spots where a derivative doesn't exist. One, if there's a vertical tangent line. Two, if there's a discontinuity, although that was technically already covered in the other part of the hypothesis. And three, if there is a cusp or corner. All right, that's where the derivative doesn't exist because the limit of the slopes coming from the left is not the same as the limit of the slopes coming from the right. Okay, and if any one of those three cases happens to be, then the function is not differentiable. Now, we can't look at the differentiability at A and at B because we need to see the slopes from the other side, and we don't know what's going on in the other side because of the closed interval. So we need to know what's happening with the slopes on this side of A and that side of B. We don't know, so that's why it's differentiable on the open interval. You see parentheses around AB, but you see brackets around the AB when we're talking about the continuity, because we don't need that for the continuity. Okay, so in regards here, we have a function which is continuous and it is differentiable. Okay, so the mean value theorem could be applied to this function f right here. However, the mean value theorem could not be applied to this function right here because we have A and we have B, and right in the middle of our interval, we have ourselves a cusp. All right, so at this point, let's call it C, all right, the derivative doesn't exist, okay? The function exists, all right? F is right here. This is our function f, and f exists. It's continuous from A to B. that part of the hypothesis is good. However, f prime of c does not exist. F prime of c does not exist because there's a corner there. The slopes from the left are not the same as the slopes from the right. So therefore, the mean value theorem cannot be used on this function, all right? What the conclusion of the mean value theorem says, and we'll get to that in the next video, that may still be true, but the mean value theorem doesn't guarantee the conclusion to happen for this function. The mean value theorem does guarantee that the conclusion will happen for this function right here, okay? And I'm going to talk about the conclusion in video number 2.